Good morning, chemistry students. Today we're going to start into some new material on the gaseous state. And normally when I teach about the gaseous state, the first thing I talk about is pressure, because gases exert pressure. And so it's important to understand what pressure is. So let's start off with the definition. Pressure is simply when you have a force and it's spread out over a particular area. So let me explain a little bit more about what this means. Force is something kind of similar to weight. Technically, it's a little different, but practically speaking, it's the same thing. So units for force would be pounds, kilograms, for instance. But technically, it's how these masses here are accelerating, and so the SI unit for force is something called a Newton. And a Newton is how quickly a kilogram of weight is being accelerated. So actually, if you have a kilogram of weight, if that weighs 1 kilogram, and it's being accelerated at 1 meter per second squared, that is a Newton. Okay, so that's what a Newton is. But practically speaking, it's kind of similar to weight. Okay, now area, you're familiar with that from math class. So area is something like square feet or square inches, where you have length and width. Okay, area is length times width, right? So for instance, if you have a room in your house and it's 10 feet by 10 feet, that would be 100 square feet. 100 feet squared. Okay, so but that's the idea of area. And so a pressure is when you have a particular force spread out over an area. And let me give you a particular example of this. So I weigh right around 160 pounds. Okay, so that's like the force that gravity's exerting on me right now. So 160 pounds, that's basically like a force. Okay, and so that'd be the force. The area, if I'm standing on 2 feet, that weight is spread out over the area that my 2 feet are occupying. And so, you know, feet are kind of strange shapes. It's kind of hard to, that's a really ugly looking foot. Let's try that again. All right, so if you've got a foot and maybe not much better, there we go. Strange looking shape, but you can estimate the area of a foot. I measured my foot just now before recording this video from the length of the tip of my middle toe down to my heel, and that was about 10 inches for me. And the width across my foot at the middle was about 3 inches. Okay, and so you can approximate the area of your foot this way by pretending it's a rectangle. Okay, and that's not true, obviously, but my foot probably occupies something pretty close to 30 square inches. Okay, because area is length times width. So 10 inches divided times 3 inches, 30 square inches. Okay, so that's the area that my weight is spread across. About 30 inches squared. Okay, and so what's the pressure that I'm exerting on the ground beneath me when I'm standing? It's force divided by area. So pressure is force divided by area. 160 pounds spread out over about 30 square inches. Okay, so Gotta add in a new calculator here. 160 divided by 30. And the units, okay, let me hit Control Enter. So I'm exerting about 5.3 pounds per square inch. Have you ever heard of the unit PSI? I'm exerting 5.3 PSI, pounds per square inch. Okay, so that's an approximation for the pressure that is beneath my feet when I'm standing up. If I'm standing up on both, actually that'd be on one foot. That's just one foot, right? Okay, what would be the pressure I'm exerting if I'm standing on both feet? Well, then I'd have two of these 30 square inches things, right? And so it wouldn't just be 30 square inches, it would be, this would be the pressure of 1 foot. If I'm standing on 1 foot. If I'm standing on 2 feet, this is an important point actually, what would happen to the pressure? Well, that same mass, that same amount of force would be spread out over a larger area. So my weight hasn't changed, but now it's spread out over 2 of these areas, which is 60 inches squared, right? You'd have 2 of these, right? And so that's 30 plus 30, 60 inches squared. Okay, that same force is spread across. And so 160 divided by 60. The pressure now is about 2.7, half the pressure as it is when I'm standing on 1 foot. Okay, so this is an important point. Force divided by area. It's the amount of force as it gets spread out over a particular area. And the more area it gets spread out over, the less pressure there is. This is pretty easy to understand, hopefully. Have you ever been lying on the floor and somebody came by and just for fun they started standing on your back, either trying to pop your back or just because they're messing around with you? If they just stand on 1 foot, it hurts a bit more than if they stand on 2 feet. And if they get up on their tippy toes, that hurts a lot more because their weight is being focused onto a smaller area. So this is the whole concept of pressure, and it's literally the origin of the unit that you might have heard of before, pounds per square inch. Okay, so when you inflate your bike tires, the bicycle pumps in the United States, so this is supposed to be a bike wheel, and then the tire here on the outside. In the United States, we mainly use PSI. And it's pretty crazy how much pressure a bicycle tire can withstand, or the way that it's engineered to withstand. My particular bike tire, I'm supposed to pump it up to a pressure. I have a road bike, so it holds a little bit more pressure, but to 120 PSI. That's pretty crazy. If you think about what that means, if you could get inside the tire and look around, if you were really, really small and you shrink down, you get inside the tire and you look around, every square inch on the surface of that tire, you look around and you find a square inch on the inside of that tire. Every single square inch in there has a pressure of 120 pounds, a force of 120 pounds on every square inch on the inside surface. So 120 pounds being pushed on it from the air, because air and gases can exert pressure just like gravity can cause things to exert pressure. Now here's an important difference about how gases exert pressure. So if you have a solid substance or some liquid, Okay, these things exert pressure because of gravity. Gravity's pulling these things down, and so you get some pressures. So gravity can cause things, basically, gravity can cause forces. I mean, it does. And those forces get spread out over area. And that leads to pressure. That's what I was just explaining a moment ago with the pressure I'm exerting when I stand on 1 foot or 2 feet. Solids and liquids can exert pressure, and that pressure is normally just downward, okay, because that's the direction gravity's pulling us because of the earth beneath our feet. But if you have something in the gaseous state, this is important to recognize. It's made up of a bunch of particles. These particles are moving in all sorts of directions. And so gases exert pressure on their own in all sorts of directions. Okay. I want to mention in passing, liquids can do this too, but you have to kind of block them into a container and then continuously try to force them more and more into a container where there's no more room to move, and then pressure can build up very quickly that way. So like in water pipes, there's pressure inside of water pipes, and they can leak in every direction because the pressure is going in every direction. But what I'm saying here is if you have a sample of a solid just out on the desk in your room or on your kitchen table, it's only exerting a force downward, and a glass of water is only exerting a force downward. But if you have some type of gas, okay, like the air in your kitchen, it's exerting pressure in all sorts of directions, and it's not just due to gravity. Although gravity is pulling it downward, the particles are going in all sorts of directions. Okay, so that's the idea of pressure. Now let's talk about something called atmospheric pressure. There's an interesting device. It's called a barometer, and the barometer was invented in the 1600s by a guy named Torricelli. So I've forgotten his first name actually, but Torricelli was a student of a really famous scientist, well-known scientist, named Galileo. Galileo studied gravity, and he studied acceleration and forces, and he was a really he's the person who is credited with first aiming a telescope towards the sun and looking at the craters on the moon. And Galileo discovered that the planet Jupiter has moons, and anyway, but one of his students, Torricelli, invented this device called the barometer. And so here's a picture of a barometer, a diagram of a barometer. So let's have a look at it. You've got a glass tube, and it's filled with mercury. Mercury is a really dense liquid metal. So it's denser than iron, it's denser than lead even. A piece of iron or a piece of lead floats in mercury. We don't use mercury too much today in the science classroom, not really at all in high school, because it's toxic and can build up in your system and cause, you know, various bad types of things to happen, mental illness, etc. You guys might remember reading about that last semester. So anyways, you have this dense liquid, and Torricelli, I'm not sure what inspired him to do this, but the way you get this set up is you start off with the tube empty. You have an empty glass tube, okay, and you fill it with mercury, and so it fills up with mercury, and you fill it all the way to the top, okay, so you imagine you fill it all the way to the top, and place your finger over the top, and then you invert the entire thing, and you place it into a pool or a tub that's already filled with mercury. So you've got some mercury in this tub here, and now you invert this thing, and it's upside down. That's terrible. It's upside down in the tub of mercury. And what's interesting is some of the mercury drains out, but then it stops. Okay, if you try this with water, if you fill a tube like this with water, flip it upside down, you'll find that the water doesn't drain out at all. Okay, it's kind of interesting. I discovered this like when I was really young, playing in the bathtub with the various like bathtub toys that I had, little boats and things and cups, and for some reason I had a cup in there. If you fill up a cup and turn it upside down underneath the water and then try to draw it out, you'll see that the water doesn't drain out of the cup. So this is something that you can try at home. What Torricelli discovered is if he used mercury, some of it does drain out, but it stops at a very specific spot every time. Okay? And so every time that he would try this, it would stop at same height every time. And Torricelli found that really curious because how's the mercury supposed to know where to stop? Why does it stop in the first place? And why is it stopping at the same place every time? And the more that he thought about that, he realized he was actually detecting the pressure from the atmosphere. Okay, so atmospheric pressure is something that most people don't think about on a day-to-day basis. If you're a pilot, you're probably constantly thinking about atmospheric pressure because there's gauges in the cockpit of planes that measure things like that. But most people, meteorologists, pilots accepted, most people probably don't think about atmospheric pressure too much. But atmospheric pressure is super important, and Torricelli discovered a way to measure atmospheric pressure with this barometer thing. Okay, so let's talk about, first of all, the force due to the atmosphere. So the pressure due to the atmosphere turns out to be quite a lot. So at sea level, if you go to sea level, that means down to the beach basically, the pressure of the atmosphere is about 14.7 psi. Okay, and that's goes without most people noticing on a day-to-day basis. But if you compare that to the pressure that somebody like me is exerting, guys, if somebody who weighs 160 pounds stands on your back on 1 foot, that's about 5 psi. Okay, and so you would definitely feel that, right? 160-pound person standing on your back. If the person weighed 320 pounds, that would still only be about 10 psi. Okay? All right, so a 320-pound person standing on your back on 1 foot, that's only about 10 psi. Okay? So the atmosphere is actually kind of like a 400-pound person standing on 1 foot on your back. That's crazy. This is the same pressure. Let's assume that that person has the same area, square inches of a foot that I do. 14.7 times the area, 30 square inches. Person weighs over 400 pounds. So let's just say same pressure as a 400 pound person standing on your back on 1 foot. That would not feel comfortable, right? That would be really uncomfortable. And yet, this is being exerted on you and me all the time, and we don't feel it. Okay, and that's pretty shocking, frankly. In other words, it's the atmospheric pressure pushing down on this tub of mercury that prevents the mercury from draining all the way out. Okay? See, if you use a tube filled with water and it's the same height, you might not see any of the water drain out because the pressure from the atmosphere is pushing so strongly, it prevents the water from draining out. Water's not very dense, but mercury, which is much denser, tends to weigh a lot more. A given volume weighs a lot more. It starts draining out, but eventually it stops at a particular height, and that's the height at which the atmosphere is able to prevent it from draining all the way out. So the pressure from the atmosphere is constantly pushing down here, and so this mercury drains out until it reaches that same height every time, because that's the height that the atmosphere can actually prevent from continuing to drain out. Okay, so the atmosphere pushes quite strongly, and we don't think about it hardly at all. Okay, so that was a surprise. There's actually a really interesting story that's described in a textbook that I have, and I've forgotten the name of the scientist, but he showed up in the court of the King of Prussia, and he had invented something called a vacuum pump, and nobody else had ever heard of a vacuum pump before, but a vacuum pump can actually pump out air, and so he had created this interesting device, the vacuum pump, but he also created a vacuum chamber, and it was basically two hemispheres that were hollowed out. So one hemisphere that was sort of hollowed out, okay, and then it was connected to another hemisphere that was also sort of hollowed out, and this was made out of iron, I think. Okay, and so basically this guy who created the vacuum pump, he brought this iron sphere to the King of Prussia, and he says, "Hey, King, open this thing up for me." And the king's like, "Okay, sure, no problem." And so, he pulls the two halves apart easily. And so then he handed it back to the guy, and so then the guy was demonstrating his vacuum pump. So he connects the vacuum pump to this thing. There's like a little valve or something on here, and he connects it, and he starts pumping out the air particles which had been in here. Pumps out the air. Okay, and so after he uses his vacuum pump, he hands this thing back to the king and said, "Okay, hey king, can you pull this apart?" And no matter what the king did, he couldn't pull the two halves of the hemisphere apart. They actually even connected this to teams of horses, and the horses couldn't pull the thing apart. All right. And so then the king was very surprised by that. And so then this guy, he came and he pressed the valve, and the air rushed back inside, and it filled the inside, and then he was very easily able to take the two halves of this hemisphere back apart again. Okay, and it was this strange demonstration of the force of the atmosphere. You see, when the atmosphere was pushing on all sides of this sphere, it's pushing with 14.7 pounds on every square inch, which is actually a lot. It's a huge amount of pressure, relatively speaking. Again, a 400-pound person standing on your back. So that's quite a lot of pressure. Okay? And it's impossible to, well, not impossible, extremely hard to pull that apart. So even horses couldn't pull it apart. But once you get air particles back inside of here, then the air particles are pushing with 14.7 psi back on all directions on the inside, and now those forces balance out, and it's very easy to open this thing up. Okay, so atmospheric pressure, when it was discovered, it was very, very interesting. And because people hadn't recognized that this huge pressure has been pushing down on us for centuries, right? For thousands of years, ever since humans have been humans. Uh, this has been all around us, and it's been like fish beneath the ocean that don't recognize that there's a whole ocean on top of them. We've got this whole atmosphere on top of us. Okay, so let me finish with a simple thought for this video. Where does the atmospheric pressure come from? Okay, well, here's our planet. Okay, Earth. Okay, so a whole bunch of solid and liquid right there. And all around Earth is our atmosphere, right? Now, why doesn't the atmosphere just float off into space? Because gravity is pulling the atmosphere down. Okay, so the atmosphere is held in place because of gravity pulling on all these gas particles. Okay, so our atmosphere is very much like an ocean of air. Okay? It's an ocean of air. And we're on the bottom of that ocean. So from another perspective, if this is the surface of the Earth, you've got all sorts of air being pulled down on us. And so here's the atmosphere up here. Now the atmosphere doesn't have a clear boundary. There's not really a clear boundary, but it's helpful if you draw it like that. And so we're literally at the bottom of an atmospheric ocean. Okay? You and me. And it turns out if you go up a mountain, there's less atmospheric pressure up there. I think Torricelli even tried experiments like this. He took his barometer device and he walked up a mountain with it, or at least some hills there in Italy. And he saw that as he would walk up the mountain, some of the mercury, even more mercury, would drain out because there's less atmospheric pressure preventing that. And as he would walk back down the mountain, there'd be more atmospheric pressure and the mercury would go back up the tube. Okay, so elevation impacts atmospheric pressure. And that's literally because the higher up you are, the less atmosphere there is above you. The higher up you are, the less deep you are in the atmospheric ocean. That's just what I call it, because that's exactly what it's like. Okay, and so then there's less atmosphere on top of you being pulled down because of gravity, and so less pressure. And eventually, if you imagine getting so high up you are actually in outer space, well, there's no atmospheric pressure in outer space because there's no atmosphere there. You'd have 0 psi in outer space, at least in deep space, once you get really far away from the planet. Okay, and so that's the whole idea. But at sea level, that's sort of, in a sense, about as deep as you can get, because after that, you can't really go any deeper. There are places around Earth that are below sea level. Okay, so let's say this is sea level here, and there's the ocean. This is ocean here, sea level. In a sense, it's like, well, how could you get deeper than sea level? Then you'd be beneath the water. There are places like Death Valley out in the west that are actually below sea level. They're really, really dry and there's no oceans nearby. And so you can actually go below sea level and stay dry if you go to somewhere like Death Valley. And there you would experience extra atmospheric pressure, maybe something like 15 psi instead of 14.7 psi. Whereas if you go to the top of Mount Everest, it's something like, you know, less than 100% of the normal pressure, like 80%. I think that's the number that's in my head. I might be wrong about that, but anyway, that's the whole idea behind atmospheric pressure.